Hello everybody. Thank you, Peter, for the invitation. Yes, I'm in the community for a while, not decades. Thanks for the compliments, Peter, even though I'm getting gray hair. My talk will be on MWEBA. That's one FP7 project, a special one. It was a joint call between EU and Japan. And you see, regarding the partners, that we have Japanese partners on the list. So these projects work like half the funding coming from the other side, here from Japanese side, and half the funding on the European side, so that in total they go up to a size of a usual strap we would have in the EU. Okay, the title of my talk is Extending the Data Cloud with Millimeter Wave Wireless Links. And MWEBA stands for Millimeter Wave Evolution of Backhaul and Access. And what I've seen on Peter's slides, I think that fits perfectly into the context of the iJOIN winter school. And let me get you into the topic, what we do in this project. The 5G motivation slides, you all seen them, so I can skip them. More important maybe, some of the things is more capacity and very high data rate links and low latency. And this is touching what we do in MWEBA. So if we look at what is currently discussed as 5G radio technologies, here the link to iJOIN, network densification. In MWEBA we address certainly spectrum extension beyond 6 GHz. Then spectral efficiency is of importance, advanced antenna systems, interference management whenever we go for spectral efficiency, and offloading. And in that context, we derived a kind of architecture or vision what we expect for the future. And you see here radio access systems marked with colors, starting in the classical IMT band, starting below 1 GHz, and going into higher frequencies, including millimeter waves. And you see you have this macrocellular layout plus many different small cells, also millimeter wave small cells. In order to handle this, we expect whenever possible to use a centralized architecture, and we call it an enhanced backbone network, which allows coordination and joint communication among these entities. The question is, if we want to go for higher capacity, how to achieve that. And you can go for spectral efficiency, more spectrum, network densification, offloading. If you do this below 6 GHz, then the potential gain is limited to about 100 or 200 times what we have today. If we change the game and go beyond the 6 GHz barrier, what we have for cellular communication at the end, then two effects will come into play. Of course, tremendously more spectrum. That's easy to understand. And if we think we go higher in frequency, the interference range of the links is getting smaller. So we can densify the network much more, having the same interference threshold. And that gives us an expected overall gain of 1,000 to 10,000. So that's the right order of magnitude where we have to go. And that's one of the main motivations why the millimeter wave spectrum is so much discussed in the 5G context. And depending on who you are talking to, you get different answers, what's important or what's 5G. So if you would ask in Korea, of course Korea, Samsung would say millimeter wave communication, that's 5G. Because that's where they are very active. Okay, there was one aspect you mentioned on energy efficiency, and there's good news. If you scale down your cells, the distance between the two antennas is getting smaller. So the path loss you have to bridge is getting smaller, and so that helps with the needed transmit power at the base station side. And if you have millimeter wave spectrum to use, then the range is really limited. You need a lot of, let's say, spatial focus, beamforming, and so that fits well with reduced power and smaller cells. So in terms of invested energy per bit you transmit, that's the right way to go for these very highly densified networks with a high capacity. Okay, coming now more into detail. So these are the partners: Tokyo Tech, Osaka University, KDDI as an operator, like Orange on the European side, Panasonic and Intel. These are the equipment providers in that project. Then we have Politecnico di Milano, Sealetti, and Fraunhofer. And it's funded by the Ministry of Information and Communication in Japan and the EU. Now, for all of you who are not so familiar with millimeter wave, just to give you a small introduction. So we have currently a couple of candidate bands which are discussed. 28, 30 gigahertz, 60 gigahertz is of interest. That's an ISM band. So we have 6 to 9 gigahertz of spectrum available, license-free. And then the E-band, 70, 80 gigahertz, which is usually a light or block licensed area. And we have to face quite challenging propagation in that region. So we have a lot of attenuation over distance, depending on the spectrum. For instance, 60 gigahertz has a lot of absorption in the oxygen domain. So communication over a few hundred meters outdoors is working quite well. But if you go really on kilometers, then different frequencies are much better suited. Then another thing is we have almost no penetration into buildings. I mean, the lower the frequency, the better you can get into buildings. I mean, Samsung showed things that they could get into buildings in Korean buildings or Korean houses. I mean, it really depends on the structures you're using. I mean, let's make one thing sure. In Germany, with all these regulations on insulation, we block our buildings. We have big concrete walls, and then we put these super modern windows, which cause 40, 50 dB attenuation for radio waves. So you have to open your window to send an SMS with LTE or whatever you're doing. You're laughing. In my lab, we requested special windows which are not coated, but they put them into a different floor. So they have good coverage from outside, and we have really to open the windows to have our 5G testbed in the lab. So that's working. So that's good and bad news, because if you have no penetration into buildings, you're well isolated if you have indoor cells. So that's a different story. Okay, and what the most important thing is, at the moment we have no comprehensive channel model for millimeter wave in general. That's really lacking. Okay, and what are we looking into in detail in that project? So we look onto backhaul, Fronthaul and the access channel. We look into the radio propagations. We build the whole idea on user plane, control plane splitting, and I will explain why. And of course, with the ultra-wide waveforms, the spectrum you have to look into waveform design, and that has to be evaluated. And hardware is, of course, a topic we look into. Okay, as I mentioned, we look into fronthaul, backhaul, and what's very new is access. I well remember 5 years ago when we built the first prototype using MIMO and millimeter wave. Peter, that was you organized the ICC conference in Dresden. When was that? In 2009? We had a prototype with MIMO and 60 gigahertz those days, and people said, you don't need that, that was indoors, never works for access, nobody will use this. Now with a demand for more access capacity, a different story. Last year at the 5G Brooklyn Summit, all companies basically agreed that now they believe it's working. Most of them had measurements, tested things, so the whole thing, game is changed meanwhile. Okay, so we also look on the access a lot in order to enable a better user experience and have these small millimeter wave small cells deployed. Okay, touching backhaul or fronthaul, or how some people call it X-haul in general, that's a crucial element in order to realize these cloud run architectures and also to have the sufficient backhaul for the access capacity. And whatever it can be, here's one picture from a recent project proposal we submitted where you have different technologies. Here you have fronthaul part, here you have backhaul, basically behind the baseband processing, while as I heard, the definition, what you call fronthaul or backhaul, is, let's say, quite liquid depending on where you do the splitting in the FiMac area. And the concept can be run on fiber, can be run on copper, as we know. Like for instance, Ericsson, they have this radio dot system where they do kind of fronthaul on copper lines, and it can be extended over the wireless link. And depending where you are, if you're in the backhaul domain, where you might use standard packetizing with a certain latency and jitter, this might not be the case, at least if you would do a wireless extension on classical CPRI, where you have everything, clock recovery and everything in a very tight framing on this level. So different requirements are to be looked into, and that has a lot of implication on how to design the air interface for millimeter wave radio transmission. Okay, coming back to the user plane control plane splitting, I'm very happy that I don't have to explain much here in that context to that audience. The important question is, you might ask, why technologies like 60 gigahertz, WiGig did not take off in the past? I mean, it's discussed almost 5 years, standardized is 11 AD for 3 or 4 years, but it didn't take off. And my personal assumption is that it was a classical IEEE technology which is in the cellular sense an alien technology. It's hotspots, and the question how to connect them. You can connect them with the EPC, the Evolved Packet Core, far down into the network, but that's like Wi-Fi integrating into it. But that will not solve the most critical problem you have if you imagine you have here a lamppost scenario and you have small millimeter wave cells at these lampposts, the coverage will be patchy. And the thing is, and we all know this from these Wi-Fi hotspots, if it's patchy, you have to find the access point, you have to log in, you have to negotiate protocols, and then you can start transmission. But if you do a control plane, user plane splitting, you can keep the control plane all the time using standard cellular communication, LTE or whatever may come in future. And whenever you approach these small cells, you just hand over the user plane. And over the control plane, you are able to provide the information on what's the SSID or whatever you use to identify these small cells. And we had a first conceptual proof of concept in 2012 at Mobile World Congress, where you could move, let's say, a small prototype in an area, and you had coverage by an 800 megahertz cell and 60 gigahertz, and whenever you were into this cell, then the user plane was handed over, and you had almost a gigabit of data rate, and otherwise it was just a few kilobit per second, because that was just a license band at 868 megahertz. Okay, will it work if you look into this context of multi-RAT and heterogeneous networks using different spectrum? We did investigation within in the project, and first of all, just to explain in more detail why we have this big benefit from these small cells. Imagine a situation where all users are attached to the macro base station. That's the user rate you can provide. As soon as we switch on some small cells and users are handed over, then you have extra capacity for these users. At the same time, you have more resources in the macro cell, and that means more bandwidth per user. So overall in that area, the macro cell users and the small cell users will benefit from this situation, given that you do the offloading into a different spectrum band. And that's here's some investigations, just the parameters. So in that context, that's our standard cell we use, and the extra bands can be at the 3 gigahertz range and in the 60 gigahertz band. And when having these additional spectrum here, 100 megahertz and here 2 gigahertz of bandwidth, then you can calculate a lot of things, as you see. Then some results which are of interest. If we assume classical average data rate per user, and these are numbers coming from an operator network, what are really existing data rates per user over the day in area, and that's expectation for future years. Then you see the blue is for the 3 gigahertz small cells and red is for the 60 gigahertz cells. Assuming we have to satisfy the demand nowadays, I mean, you can introduce small cells, no matter what frequency they are operated. They provide extra coverage, extra capacity, but I mean, the system rate will not increase dramatically given this demand. But since demand is increasing, already in 5 years' time, it is expected that at a certain number of small cells base stations, we have a dramatic system rate increase, and in 10 years' time, you see with about 30 base stations per macro cell using millimeter wave technology, we can provide the 1,000-fold capacity, which is also needed at this time. Okay, so the 1,000 times capacity can be achieved with this concept, and already halfway in 5 years' time we will have significant benefit from these small cells, even if the coverage is quite patchy. Okay, one important thing is that we have these dual connectivity in order to support the seamless handover, and then we have to dynamically operate these small cell base stations. I mean, I'm not going into detail of this. I expect that we will hear more about this from the iJOIN project. Dual connectivity, we believe, is key, and that's supported much better with this control and user plane splitting. And in one vision, one application scenario, I saw it on one of the pictures before, you have a macro base station, you have these small cells working together, and everything is orchestrated by the Cloud RAN, where all the resources are used and coordinated. And that might be one application scenario we are discussing in the project. Very dense user crowds. An example for the Tokyo 2020 Olympics, you might have 2 Cloud RANs run by 2 different operators. They have macro base stations around, and in the end you want to provide the highest capacity which is achievable in that area. And you will add Wi-Fi hotspots and millimeter wave small cells in order to boost capacity. They have to be coordinated, especially these access points using the free spectrum with a virtual network operator, and then depending on who's doing the offloading, you can do charging and billing in that context. And given that, with an extra capacity, you can provide location-specific content for the users in order to enhance the experience at the event. Okay, but will it work? That's the question. And in order to understand this in a better way, we did a lot of channel measurements to address the question of building a comprehensive channel model in that context. Here are some examples what we did in Berlin. So in Berlin we have not all these high-rise buildings like in Asia or in the US, but we have a few. So we went into the center where we have the Sony Center and did measurements. So that was our small cell base station put on 3 meters height, and that was, let's say, like a user moving around. So that was a trolley, you could move along the road, and we did a lot of channel measurements. And in order to have a good understanding, does it match the expectation, what are we seeing here, we have this accompanied with ray tracing simulation of that scenario. You see the buildings here and the passes of what happens if you have cars moving. So we have the full angular information. And that allows us to derive a 3-dimensional time variant channel model. And that was done in that scenario. Another situation is a campus scenario, quite open. That was here measured in Nizhny Novgorod in Russia. So Intel, they have a subsidiary there for research. So we also had measurements there, where you see the passes like here, the direct path and the reflecting waves to be measured. And then you see here the measurement passes. This can be put all together. And before going into the results, what we learned from it, I will show you how such a measurement scenario usually looks like. So you put the antenna at a lamppost at one side, and then you move at the other side, and you just record these measurements and do post-processing after. The question is, what happens if you don't move at all? So the question is that a static channel or not? Some researchers say yes, and given that they do very selective angular measurements, so they move the transmitter and the receiver into different positions and measure, and they claim nothing changed on meanwhile, and if nothing would change, they're right, you can superimpose these channels and you have the full angular spectrum of channel impulses. Okay, what you will see here in a few seconds is a measurement with omnidirectional antennas in such a inner city scenario, nobody moving close to the antennas, it's just the surrounding which causes the changes of the transmission behavior. And what are we seeing? That's the channel impulse response, so that's a direct path and that's reflections. And then we take the 4 strongest paths and order them and observe them over time. And while we are recording this, you see from time to time certain passes will be attenuated significantly. And if you look when it happens, then there are moving objects around. So even though they are 5 or 10 meters away, they have a significant impact on what is happening in the channel. And imagine you would separate the measurements looking with horn antennas into different directions at particular times, you would not capture these effects, which are relevant in such scenarios. Another question is blockage. Here we have the transmitter and receiver on the same situation, and this gentleman is crossing the line of sight. You see that the line of sight pass, the black one, is really strongly attenuated, but at the same time the other multipass components, they don't care. Meaning that if we better understand the channel and if we can match our transmission strategy into the second strongest pass, then we have just these 5 dB loss while the line of sight pass is blocked, but not 30 or 40 dB loss because we have blockage. Okay, so reflections, strong reflections over different directions behave independent in the sense of blockage. The question next is, what's on long distance? What happens if you really go beyond a few hundred meters? And for this purpose we used one of the old army airports in Berlin, which is meanwhile a museum. You can see the airplanes here in Gato, and we could use the runway and we could drive away, and the two there is just a line of sight and a single reflection from the ground at larger distance. And we measured this on the runway, on grassland, what's the impact on that. And interestingly, if you have a two-ray model, of course you expect that the two passes superimpose, and sometimes they add up and sometimes they subtract. So you see this structure, and the further you go, the longer the distance, then this modulation over distance is going longer to have a negative or positive superposition. Okay, and the same happens if you vary the height of the antenna on one side. So that works quite well, so that's supporting the modeling approach we had. Another question is, do we have to measure at every frequency band again? Do we need measurements campaigns for 29, 27, 31, 33 gigahertz? Yes or no? And that was one of the big questions, because from physics we expect that the direct passes, they are frequency independent, the reflections as well. The big difference is the multipass component. And we could confirm with measurements we did for METIS at 10 gigahertz and at 60 gigahertz that basically also for these two frequencies the main multipass components are independent on the frequency, just the attenuation depends on the frequency. And in some recent measurements we did in December, we could show that using directive antennas and adaptive antenna arrays at two sides, we can really see that if the two antenna arrays match each other on the multipass component, that we have a strong attenuation, otherwise you don't see each other. So this is one array provided by Intel in that context, which has 128 elements, which allows really very narrow beam steering between the transmitter and the receiver. Okay, derived from the measurements, as I said, we have these directed paths. These are very deterministic components and then statistical components from far distant reflections. We derived a channel model in MWEBA, also considering blockage, which was here measured. And this is all added up in one comprehensive channel model. You can have a look on this. That's for download, available at the website, and giving more insight into these channel properties if you're interested in that aspect. Okay, maybe to conclude this thing, we need special antennas for this. Classical scenario for backhaul and fronthaul. Nowadays we have like dish antennas to focus the energy. Usually they are bulky, take a lot of room. So we came up with a solution having these planar antennas which have the same effect. You see here the directivity of the antenna, and depending on the size you can steer the directivity 25 dBi, 35 dBi, so you can make these antennas quite directive, and that's very good for these fixed directive links for backhaul and fronthaul. Okay, and once you want to follow with your beam the user mobility for an access scenario, you need active antenna arrays, as I mentioned, and then you can form with an 8x8 antenna array such nice beams and can follow the user. Okay, and what is expected? MWEBA is now halfway through. What's expected next year? Really to have prototypes. So we will have millimeter wave chips for the UE at Mobile World Congress next week. We will have a joint demo with the Panasonic guys where you really see USB sticks you put into your laptop, and then you have almost 2 gigabits per second between laptops. As a range extension with the antenna arrays, you can do this over 10 to 15 meters. So that will be at the booth. So we have a few meters between ours. And then another thing is that antenna array by Intel will be shown. And next year we will have a fully fledged demo where we have the user plane, C-plane splitting between the macro E node B in the lower frequency band and the user plane at 3.5 and 60 gigahertz operated. Okay, so what did we learn so far in MWEBA? Of course, there is a huge potential of millimeter waves that can provide the higher data rates and reduce the energy per bit when we transmit. We did a lot of channel measurements that we got new insight for accels and backhaul scenarios. We could also show some proof of concept that these adaptive antenna arrays at millimeter waves already work. And a new quasi-deterministic channel model was derived that's based on these measurement and ray tracing. And we can confirm there are a lot of challenges on the network side, on network management, reconfiguration, then the whole story on reduce the energy consumption if you have these heterogeneous networks, and how to enhance finally the user experience. In order to make you believe that there are a lot of people behind, here's one of the team pictures at one of the meetings in Osaka in 2013. And yeah, in most organizations also students are helping to in that context. So that concludes my talk. Thank you very much. I'm happy to answer questions.
Very illustrative. Very amazing. So any questions from the audience first?
I have a question. You mentioned that the dual connectivity is an essential part to be looked at. Can you say something where you would foresee the anchor point there? Because I assume that the basement part of the millimeter wave you would be able to put very locally, but in a pool within zero. Can you say something?
Yeah. Dual connectivity is key when we assume that we have a patchy coverage, meaning we put the anchor for the control plane on full coverage, which is here given with a 3G or 4G network. And where to split the user plane, that's still under discussion. I can give you my personal view on where I see it might be quite a reasonable split. If you look at all the signal processing which happens in physical layer, you have your data, your packets, and then you do forward error correction, then you do puncturing, then you have these packets, and then you start to schedule them and send them somewhere. If you would split at this point, before going on modulation or whatever, then you would have a data queue which is already encoded, and then you just take these encoded data to a different path and a different air interface. And then you're flexible, whatever air interface you're using. Can be single carrier, OFDM, whatever you're using on this millimeter wave air interface. And the cool thing is, if you get a hybrid ARQ request, it's the same entity sending it. And if your millimeter wave link has failed meanwhile, then you send it the user plane over the LTE network. You take longer time, but you know which packet to repeat. So, and if you imagine everything is in the cloud run, then you would say, perfect. I believe you would say, yeah, that's what we support anyway. Yeah, but that's more my personal view. That's different people might have different point of view on that.
Interesting. Any other questions from the audience?
Maybe this is dual connectivity. But actually, if you have one link which is higher, much quicker, much faster than the other one, if you really would split the user plane, then one slows down with the other one. So it's like, so you have to make choices for the user plane so that you don't say put penalty on the higher throughput.
Yeah.
Because I think that the band is much larger.
Yeah.
And the throughput will be much larger. Potentially the speed
Yeah.
will be different.
Okay, that's right. You need a lot of, let's say, content-aware management on when to switch the user plane. I mean, in the consortium, I don't know if that's available on YouTube, the Panasonic guys showed in an experiment where you had a video download, you did this constantly over a 3G or 4G network, and then in another test, they just passed by, just moving by that millimeter wave link, and then really in an instant you filled your buffer for the video, and that took a lot of burden on from the LTE network. I mean, of course, if you're assuming that your 1 gigabit per second is your baseline you want to support, if you lose that, of course you are degrading in throughput. But here the idea is you have certain services which benefit a lot when you have sporadic high capacity bandwidths available.
It's more a kind of, let's say, switching really the user plane from one technology to another, rather than split the flow of the user plane. Right? So kind of better splitting.
Okay, that's what you mean. I think that I'm not an expert in protocol layers, but I can imagine that depends on the application. If it can support a splitting of content on different layers. I remember we did things on scalable video coding, where a certain base layer was transmitted over one technology and additional packets which enhance the video experience were transmitted over a different air interface, and when available the user could enjoy a better picture. Otherwise you had this, let's say, a standard resolution of the picture. But the picture never stopped, which was important for live streaming of football events. You don't want to miss the goal.
Particularly the German goal side.
Yeah.
So how long are you still here tomorrow?
Yes.
Great. So if you have further questions, I think Thomas will be happy to answer them offline. And
My pleasure.
presentations will be available also on the website. We're actually recording them.